Hello everyone, my name is Tejas and the topic that I'm going to discuss today is eigenvalues and eigenvectors. Alright, so let's start with the definitions. Eigenvalues, suppose we have a vector x that does not change the direction when multiplied to a matrix A is known as eigenvector of the matrix A. So let's think about it. So suppose we have a vector which is two-dimensional. So as we know that a two-dimensional vector could be plotted as a line on a xy plane, right? So suppose we plot the vector, we get a line on a two-dimensional plane. So if we plot another line and the slope of those two lines are the same, then we could say that those two vectors are actually in the same direction. It's just that their magnitude could differ in some way, but they are in the same direction. So let's take an example, for instance. So we have a matrix A which has the elements 8, 3, 2, and 7, and we have a vector x which is 1 and -1. All right. So we multiply those two, the matrix A with the vector x, and we see that we get 5 and -5 as another vector. So if you notice that if we could take 5 outside, or we could factor out 5 from that vector, so essentially the direction of that vector did not change. It's just that the vector got multiplied by 5, or the vector was scaled by 5 units, in the sense its magnitude increased by 5 units, but the direction is still the same. All right. So yes, x increased in magnitude by a factor of 5, but the direction remained unchanged. Hence, x is an eigenvector of A. So we just followed along with the definition, and based on that definition, x is an eigenvector of A. And now let's move on to eigenvalues. So suppose, again, we have the same vector and the same matrix. So we did the multiplication A times x, and we got 5 times x as the answer because we factored out the 5 in that case. So an eigenvalue lambda is a factor that explains the change in the magnitude. So if we go back to the previous slide, we can see that the magnitude of x has been multiplied by 5, and so it's 5 times x right now. So the factor that changed the magnitude of x is 5. So that tells us that 5 should be the eigenvalue of this matrix A. All right, so yes, as we follow along with the definition, Ax equals 5x, therefore lambda equals 5 is the eigenvalue of A. And so this gives us the basic equation of eigenvalues and eigenvectors, which is Ax equals lambda x, where x would be the eigenvector and lambda would be the eigenvalue. And lambda is a scalar in this case. So just like 5 is a scalar in the example, lambda should be a scalar. So moving on. So let's discuss the steps to find eigenvalues and eigenvectors. So all of this is derived just from the basic equation that we mentioned earlier. So it's Ax equals lambda x. So we subtract by lambda x on both the sides, so we get Ax minus lambda x equals 0. Right? And then we can factor out x on the right. So we get a minus lambda times I times x equals 0. So let's see how what else could we do with this equation, right? So let us assume that a minus lambda I times x equals 0 has a non-zero solution, right? So that should tell you that a minus lambda I is not invertible. Hence, the determinant of a minus lambda I should be equal to 0. So this is something that we discussed in the earlier sections, I guess section 5.1 and 5.2. So if a matrix is not invertible, then its determinant is equal to 0. So hence we obtain the characteristic equation determinant of a minus lambda I equals 0. Okay. So now the next step is to find the roots of the equation. So once we find the determinant of a minus lambda I, it will be in the form of an equation, and we need to solve that equation in order to find lambda, or we need to find the roots of lambda. And those roots of lambda would be the eigenvalues. Alright, so the third step would be to plug in those eigenvalues in that equation to get the values of each lambda corresponding to the eigenvectors x. Okay, so now let's see an example just to make it more clear. Okay, so problem 1. So find the eigenvalues and eigenvectors of a matrix A, which is 2, -1, -1, 2. Alright, so in this case, this is just a basic example. We took a 2 by 2 matrix. So the first step is to find A minus lambda I. So what we do is we just take the matrix A subtracted with lambda times the identity matrix, which is 1, 0, 0, 1. Okay, so we get 2 minus lambda, -1, -1, 2 minus lambda. So you can notice that if this was a bigger matrix, all you had to do is you had to subtract lambda from the diagonal entries and leave the off diagonal entries as it is, like, because as you notice in the identity matrix, we have zeros in the off diagonal entries. So we are not changing anything from the off diagonal entries in the matrix A. All we are changing are the diagonal entries in the matrix A. Okay, so now once we found A minus lambda I, now we compute the determinant of that expression. So as this is a 2 by 2 matrix, we don't need to worry about anything. This is just the direct formula. All we have to do is we need to multiply the diagonal entries and subtract them by the product of the off diagonal entries. So we multiply 2 minus lambda with 2 minus lambda, and then subtract it by the product of -1 and -1. So that after simplification, it gives us the equation lambda square minus 4 lambda plus 3. So now this is a quadratic equation, and we need to find the roots of this equation in the next step. So yes, next step is to find the roots of the equation. So I'll use the method of splitting the middle term. So what I'll do is I'll split -4 lambda into two separate terms so that I can take lambda, I can factor out lambda somehow such that we get a proper factorization. So I split -4 lambda as -3 lambda minus lambda. Then I factor out lambda from the first two terms. So I get lambda times lambda minus 3. All right. And now for the second two terms, I factor out -1. So I get lambda minus 3. And then finally, I'll factor out lambda minus 3 out of these two terms. So I'm left with lambda minus 1 times lambda minus 3. So this would tell you that the two roots would be lambda minus 1 equals 0 and lambda minus 3 equals 0. That should tell you that lambda equals 1 and lambda equals 3 are the two eigenvalues of A. So that completes step 2, in which we are able to find the eigenvalues of the matrix A. Now the next step is to find the eigenvectors. All right. So plug in. So we denoted the two eigenvalues as lambda 1 equals 1 and lambda 2 equals 3 so that we could differentiate between those two eigenvalues. Right. So we just changed the notation a bit. We took lambda 1 as 1 and lambda 2 as 3. And now we'll plug in the lambdas in the equation A minus lambda I times x equals 0. So we just need to plug in lambda 1, and then once we find the values, we'll find the corresponding solution to x. That would be our eigenvector for lambda 1. And in the next step, we'll plug in lambda 2 equals 3 into this equation, and that will give us the eigenvector for lambda 2 equals 3. All right, so for lambda 1 equals 1, we have A minus I times x equals 0, because we just plugged in lambda 1 in the place of lambda, which is 1. So this should tell you that we have A minus I times x equals 0. And this should also tell you that x is in the null space of A minus I. So this is from something that we did earlier in chapter 4. And then, so A minus I would be 2 minus 1 minus 1, 2 minus the identity matrix. So once again, we just subtract 1 from the diagonal entries, and we get 1, -1, -1, 1. Okay, so now let's recall how we found out special solutions. So earlier when we were discussing the null space of a matrix, the steps followed along in a way that we first find the special solutions, and then those special solutions become the null space of the vector x, or of the matrix A, right? So so we follow along the same steps. All we have to do is we first simplify the matrix A into a reduced echelon form. So all we have to do is we first see that we have the first pivot is 1. So now we get rid of the second entry, the negative one, which is below 1. So the second entry in the first column. Alright, so we do the operation R2 plus R1. So that helps us to eliminate the entry which is below the first pivot. And now as we get the reduced echelon form, we'll use that form in order to get the special solution of x. So I denoted the elements of x as u1 and u2 just so that we don't mix up the notations. If I took it as x and y, then we're already specifying the vector x, and like it gets a bit messed up if I do it that way. So I just for simplicity I took it as u1 and u2. So then this should tell us that the first element 1 is the pivot. So the first column should be the pivot column, or the pivot variable. So u1 is the pivot variable, and then and then that should tell you that u2 should be a free variable because there's no pivot in the second row. As we don't have any pivot in the second row, u2 would be a free variable. So let u2 equals t because it could take any possible value as it's a free variable. Then when we do the matrix multiplication, we get u1 minus u2 equals 0. So as u2 equals t, we take it as u1 minus t equals 0. So that tells us that u1 equals t. Alright, so then we have u2 equals t and u1 equals t. We factor out the t and we get 1, 1 as the vector. 1, 1 times t as the vector for all t belonging to R as possible solutions to x. Okay, so this 1, 1 vector is actually the special solution to the matrix X, and then the eigenvector of A for lambda 1 equals 1 is x1 equals 1, 1. So that special solution is now the eigenvector of A. Okay, so now again we follow the same procedure, but this time we'll take lambda. Okay, so this should be lambda 2 equals 3 and not lambda 1 equals 3. So this is just a typo, because based on the earlier notation we took lambda 1 equals 1 and lambda 2 equals 3. So we have a minus 3ix equals 0. We plugged in lambda 2 equals 3 here. So this should tell you that we just subtract negative 3 from 2 and negative 3 from this 2. So we get negative 1 as all the entries of the matrix. So now we follow the same procedure in order to get it into a reduced echelon form. We do R2 plus R1, and then again we do the matrix multiplication. We get negative u1 plus negative u2 equals 0. u1 is a pivot variable and u2 is free, so let u2 equals t. Then negative u1 minus t equals 0. u1 equals negative t. Okay, so now this, after factoring out t from those vectors, we get t times 1 times negative 1 for all possible values of t, right? So then again this vector 1 comma negative 1 is a special solution, hence the eigenvector of A for lambda 2 equals 3 is x2 equals 1 comma negative 1. So that was all for problem 1. We just followed the steps of finding eigenvalues and eigenvectors. Okay, so let's move on to problem 2. So for the same matrix A, find the eigenvalues and eigenvectors of A square, A inverse, and A plus 4i. Okay, so before we move on to these problems, so let's basically derive the expressions for basic equations for a square, a inverse, and a plus 4i. So consider the basic equation ax equals lambda x. So we pre-multiply a on both the sides. So when we pre-multiply a on both the sides, we get a square x equals a times lambda x. So now as lambda is just a scalar, we can factor it out because it's just a scalar. If this was a matrix, then it might not be allowed in most cases. But because it's a scalar, we can factor it out, and the multiplication a times x is allowed, right? So now we plug in ax equals lambda x back to this expression. So a square x equals lambda times lambda x. That gives you a square x equals lambda square x. So the basic equation for a square x is lambda square x. So that should tell you that the eigenvector of a square is x, but the eigenvalue is lambda square and not lambda. So eigenvectors of a square are the same as that of a, but eigenvalues are lambda square. So the eigenvectors did not change. In the earlier case, it was x, and in the same case, it's again x. So, but the eigenvalues are now squared because of a square. So based on the previous example, the two eigenvalues were 1 and 3. All we have to do is we have to square the two eigenvalues, and that should be the eigenvalues of a squared. So they are 1 and 9 in this case. And the eigenvectors remain the same as I just discussed earlier. For the eigenvectors x1 and x2 are the same as problem 1. And we can generalize this property as a to the power n times x equals lambda to the power n times x. And then eigenvalues of a to the power n will be lambda to the power n. So following the same argument, you can pre-multiply by a again and again until you derive this expression a to the power n times x equals lambda to the power n times x. So yes. Okay, so before we continue to so let's end this video here. So if you have any questions, feel free to ask your TA, and then we'll continue with the problem section in the next video.